Hello, everyone. So this is the second example we will solve. It's quite substantial. It's a deep excavation. As you can see here, we have 27.5 meter deep excavation, and we have here the retaining wall will be made of board soldier pile that's 1050 millimeter in diameter and the spacing 2.6 meter. So basically we will have a pile every 2.6 meter, and the spacing in between will be shotcreted. So we call this system of retaining structure soldier pile, which can be made of board pile, for example, or can be steel hitch section. It depends. So basically you will have here also one, two, three, four rows of drilled and grouted ground anchors that actually the spacing here is not 6 meters, it's 2.6 meter. That's quite, so it's 2.6 meter. So we will have ground anchor. The ground anchor would be made of two parts. One part will be the free length, which is not in contact with the soil, plus the grouted length. We will have here the design so that the free length is 15 meter and the grouted length will be 10 meters. Obviously, this can be designed outside Plaxis, and then you input the parameters to Plaxis. The ground profile, there will be some work that must have been done before arriving to that stage. And we have here ground profile is made of fill. You can see here the fill is 3 meter thick, followed by soft clay. Soft clay thickness is 2.5 meters. And then we have calcarenite between 5.5 meters and 18 meters. That's 12.5 meter thick. And this is followed by conglomerates. Calcarenite is basically some sort of cemented carbon material, and the conglomerates is also some type of rock. So, and here would be having a dry excavation because the groundwater level here is at -3 meters. So you have water that's covering the whole site, and but we will be doing some watering so that we can do dry excavation. I'll be back and forth between this important slide and also Plaxis. So if we have Plaxis, I have the model here already created, but we will start this from scratch. So first, we need to see the dimensions of the model and also the project properties. So this would be plane strain versus axis symmetric. This is plane strain, would be 15 noded elements. Now for the width of the model, this 20 kPa applies over like say 50 meter or so. So that side of the model is about 100 meter, and that side of the model would be close to say 40 meters. So I can come here and say, okay, I will have -40 meter and I would have 100 meter. Now uh, for the y dimensions, so we have here the excavation, or we'll say the pile 2 is -34 meters, so we need enough material underneath it because to avoid basically the boundary effect. So let us say that we will have the maximum at the top would be 0, and this will say -60 meters, so the depth will be -60 meter. So basically this will just give you this drawing area which you can control. What did I do? We'll repeat this one again. So so this is a new project. I'm just repeating myself. We said here this is minus 40, and this is 100, and this would be -60, and this would be 0. And if we say okay, you see that basically you have this drawing area. Press escape, so you have it here. So let's start by using borehole tool. This is very similar to the first example with it. We will create a borehole at this here. This is our 0, 0. So make sure that you are in the soil tab, and okay, press this one here, create borehole. I come here, this is has to be the 0, 0, and this you can basically snap to whatever you like with the grid, and you can basically control the grid spacing here. We have here every 0.5 meter. So I will actually go to 0, 0, press, and now I have the borehole window. Nothing new here. So I will add first from top 0 to -3, and this would be basically the fill. So the thickness of the fill is 3 meters, so I have -3 meter. I'll add another one from -3 to -5.5. You must have this outside ready for you to enter, to input inside Plaxis. And this has from -5.5 to -18. You can see when I say add, it creates actually the top of the layer automatically from the bottom of the previous layer. So I have here -18, so I would say -18, as you can see, and then I have the conglomerate will go to say -60. All I have done so far is just to create these layers. I have not created the material list yet. Now, important to see, okay, the groundwater level here is at -3 meters. So I would say here it is -3. You see what will happen to the groundwater. So far, I'm happy. I have not created any materials. I can say, okay, and you can see here now, this is my 0, 0, okay, at the top. Well, you can design it the way you like. Whether the origin of the XY axes would be at the top or at the bottom, that's up to you. But if your project has certain level style, people call it RL, it's a good idea to follow the RL style of the stratigraphy or the ground profile that you have. Now let us create the material. So we'll create a material first. The material, we'll call it fill. So this would be the fill. As you can see, this is the fill. And we will, you must have the design geotechnical parameters. You must have a table of that nature outside. In this example, I'll use in Plaxis what we call the hardening soil model. That's different from more column model. HS here is for hardening soil model. I'll use the hardening soil model for the fill, for the soft clay, for the calcareonite, but for the conglomerate, I'll use more column material because the material is expected to be relatively kind of strong and stiff, but that it's your choice. Uh, this is a completely different area in numerical analysis or in geomechanics that you may need basically to perfect. So I have here the material parameters. So as you can see here, I'll try to reduce this so that I can see it on the side. Hopefully I can. Well, I may need actually to reduce the whole thing here so that I can basically uh, navigate back and forth. So okay, so we can reduce this thing here and we can increase this thing here. Okay, like I said, you need this is a important field in soil mechanics or geomechanics that you need to know, or you may need some help if you are a numerical analysis person. It's a very good idea to know how to derive these parameters, or you work with your colleagues basically to determine this. So, okay, back to this. So I will create, let's new, and I will call this material as fill. As you can see here, soil model. So I go to soil model and it will be the hardening soil model. So hardening soil model. And I have here all the parameters ready. Gamma bulk is 22. So I will assume that the gamma above the groundwater is the same as below the groundwater. So I will go to mechanical and I have here, let us just increase this a bit. I'm in the fill and I have here E50, as you can see here, that's 50, that's megapascal, so 50,000. And E odometer, well, take this like the way I do it for now, and hopefully I will explain the differences and how to handle the hardening soil model in a separate video. But for now, let us continue our journey. So that's 50, 50, and this is 100. Power is 0.5. Should have the power here somewhere. Okay, power M, as you can see, it's 0.5. By the way, this is supposed to be new N. It's Poisson's ratio. Poisson's ratio is 0.25. We can put here as 0.25. Okay, so C dash reference, so this is 0 because this is a fill material. Phi dash here is 38, and I have a dilatancy angle here, science, it's 5. This material is drained, so you can use dilatancy angle without much fear. This is drained material. Why I say fear? Because if it is undrained, you must be very reluctant to use dilatancy angle, because this theoretically can give you infinite strength. So you have to watch for that. And the tension cutoff, no tension cutoff. So now if I go to interfaces, interface here strength is 0.7. We explained this in the previous video. That's 0.7 because I will have a foreign material that's in the form of piles into the soil. So I'm saying here that the interface strength will be 70% of the material strength. Now the initial, you can see here K naught is 0.6, so I will go manually and I use this as 0.6. This K naught here is what the software will use to determine the geostatic lateral or horizontal stress from the geostatic vertical stress. When I say geostatic vertical stress, I'm referring to the effective. We go back here. So as you can see here, these are default values. K naught normally consolidated. This is a constitutive parameter that's different from what we are using here. So mechanical, at this stage, we don't have groundwater flow or anything, so perhaps we may not be interested in the permeability for now. Later we may do consolidation. So this is a fill material. So I'm done with the fill material, as you can see here. So that's done. I can basically even copy this for the soft clay. Soft clay, we change the color so that we are close to what we are using. So I will call this soft clay. Okay. Now, soft clay is a beast in itself. I will not go into the details here of how to handle that. But for the time being, it's hardening soil model, and we will use undrained method A. Like I said, this is completely topic that I hope I can cover it in one video. So undrained A, you will see now what parameters Plaxis. So this is 18. What are parameters Plaxis will give me to input. So take it. So it's telling me here the undrained shear strength is 30. If you are inputting the undrained shear strength directly into Plaxis, like if you use method B, for example, so you would enter the 30 kPa. But because this is effective stress analysis for the undrained conditions, we will be entering the equivalent C dash and phi dash. So here it's telling me phi dash 25. I don't have any dilatancy here. C dash is 0. So basically this combination, pay attention to this. This combination of C dash and phi dash will give me the equivalent 30 kPa somehow. So you must have done some sort of calibration process to come up with the parameters C dash and phi dash that give you the design 30 kPa that you have determined before starting your numerical analysis. So I will also need to adjust E50. So it's telling me E50 here is as small as 1500. E odometer is also 1500. And the unload reload is basically 3500. So I will continue interface. We have interface strength 0.7, and here K naught is 1 for some reason, so it's 1. Go back to mechanical, just make sure that we got this right. So no tension cutoff, 1500, and at 1025. So I'm happy with this one, and the color is okay. So I created the soft clay. Remember, we are talking about how many layers we have. So we have here 1, 2, 3, 4 layers. So the next layer would be the calcarenite. Calcarenite is still the hardening soil model. So I can go to the fill and copy it, or I can start from the beginning. So copy, and I will call this say calcarenite. Remember, we said calcarenite is some sort of cemented material. It's hardening soil model, and it is 20, so it is 20. Go to mechanical. So basically, we have here E50 is 150, so this is 150,000 because it's 150 megapascal, 150,000, and then this is 300,000. Poisson ratio is 0.25. We have it here 0.25. What else do we have here? We have the power is 0.05 because this is cemented material. So we don't have this. What is the power here? The power is 0.05. You need to pay attention to this. If you have cemented material, normally M would be relatively small. M reflect how much the stiffness will be affected by the effective stress. A P reference here is 100. I forgot to mention this. Like I'm saying, all these parameters belong to horizontal effective stress, or the minor principal stress effective sigma 3 of 100 kPa, and the software inside would interpolate or extrapolate based on the actual value of the sigma dash 3 in the software. Now back to the parameters. I have here C dash is 250, so I'll put here 250, and the friction angle is 32, I'll put 32. Remember, we said this is cemented material. For now, I am not putting tension. You need to be very careful when you have tension strength in excavation, because when you have tension, it means that the material doesn't need support. It's the other way around. It's actually will drag the retaining wall inside the soil, not outside the soil, by the tension component. So you have to be very, very careful in situations like that. So I have 150, 150. This is incorrect. So let's fix this to 150. Sometimes the program can really give you a warning if the set of material properties you input is not consistent with what's normally considered. So 250, 32, we don't have any psi. Interface strength is still 0.7. I have it 0.7. And the initial K note here is 1. So I'll use this one and say this is 1. And we choose basically the color. I'm happy with this. We called it calcarenite. So what would remain is basically the last one, which we said it's going to be more column material, so it's conglomerate. So I can copy this and I can call it conglomerate. We know it's conglomerate is type of rock, and we said it's more column material and it is drained, and the material has 22 kilonewton per meter cube. So that's 22. These parameters are not important within the context we are using. So E dash reference is 350 megapascal, say 350,000, and we have here Poisson ratio is 0.25. What else we have here? So the material has also 250 and the 32. So everything is done here. Interface strength is 0.7. The initial, this is K not initial, that's manual. That's so basically I have now all the materials. That's very good news. Obviously, you need to review this very carefully, and then um, move to the next level. So what I need to do now is I can now go to this and I say, okay, in the top I have the fill, and below it I have the soft clay, and below it I have the calcarenite, and the conglomerates is last. As you can see here, now I have created my ground profile happily. Like I said, you always a good idea to go back and review. You review the borehole, very important, and also you review the various material properties in case there is an issue. So I think I will stop this part here and we'll continue in part 2.